Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on motor effect and electromagnetism. This question is from October-November 2021, paper 4, variant 1. In this lesson, we will discuss how to define Tesla in a proper way. We will also discuss how to find direction of force and magnitude of force on a current-carrying conductor inside uniform magnetic field. At the end of the lesson, we will discuss one very important concept about torque experienced by a loop inside uniform magnetic field. For part A, we need to define Tesla. So what is Tesla? Tesla is unit of magnetic flux density. Simply, we can say unit of D means unit of magnetic flux density is Tesla. And the symbol we use for Tesla is capital T because this is after name of scientist. So we use capital T for Tesla. Now let's try to understand how we can define Tesla. Imagine that we have a uniform magnetic field. So this is uniform magnetic field, and inside this uniform magnetic field we place a wire. So let's say this one is the wire we place inside uniform magnetic field, and there is current in this wire. If the length of this wire, let's say from here to here, means the length of the wire inside magnetic field, let's say this length of the wire inside magnetic field, so I will simply say L inside magnetic field, if this is equal to 1 meter, and current in the wire means I in the wire, if I in the wire is equal to 1 ampere, then we can define magnetic flux density. So first of all, let's try to understand the formula for magnetic force. Magnetic force F is equal to BIL sine of theta, and theta is the angle between B and I. So this is the angle between B and I. Now, if the angle between these two is 90 degrees, so simply we can say F is equal to BIL because sine 90 is equal to 1. Angle between B and I in this case is 90 degrees, so sine of 90 is equal to 1. So we can also write down here sine of 90 is equal to 1. Now we need to define B. So we can rearrange this one. We can say B is equal to F over I times L. Now, if I is equal to 1 amps, as we have mentioned before, if this is 1 amps and L means the length of the wire inside magnetic field, this is equal to 1 meter, and the force experienced by this wire will be 1 Newton. Then in this case, the magnitude of B means the magnetic flux density. This one will be equal to 1 T. This will be equal to 1 Tesla. And that's all what we need to understand to define Tesla. So let me explain you how you can write down your answer. One thing more you need to understand. Tesla is a unit. So you have to define this one in terms of units, means using units. This is how you can write down your answer. So in this case, you can see you have to mention that 1 meter, the unit length, current carrying wire of 1 ampere, experience of force of 1 Newton in a direction at right angles to both the flux and current. If you mention these points, you will get 2 marks for this question. Let's try to understand a little bit more about magnetic force, especially how we can write down this one in vector form. In vector form, we can say FB, this is equal to I times L cross B. In this case, L is also vector and L is called length vector. So this is a vector quantity now. We will be treating this one as a vector. And it has the same direction as direction of current. So simply we can say its direction is in direction of current. Very important point. In direction of current. And this order is also very important because if you find L cross B using right hand rule, you can find direction of the force. So it has to be L cross B. You can now write on B cross L. If you do B cross L, direction of magnetic force will be wrong. Now if we expand this one, we can say this is equal to ILP sine of theta. And theta is the angle between L vector and is the angle between B vector. Current in fact is scalar. So theta is better to say this is the angle between L vector and B vector, not the angle between I and B. But magnitude of angle is the same. But this is a proper way to say theta is the angle between L and B vector. Now what is direction of L vector in this case? Current is up, so direction of L vector is also in direction of current. So this is also direction of L vector. So the angle between L vector and B vector in this case is theta. I hope this is clear to you how to write down magnetic force in vector form. And theta is the angle between L and B. For part B, it is given to us a stiff wire is used to form a frame, and dimensions of the frame are 8.0 by 6.0 centimeters. So one side of the frame is 8 centimeters and other side is 6 centimeters. And current in the frame is also given. Current is equal to 5.0 amps. It is also given to us that magnetic field lines are horizontal and the angle between magnetic field lines and PQ is 50, as you can see here. So the magnetic field is in the horizontal plane. Very important point. It is also given to us when side PQ first enter, means just enter the magnetic field, the reading on the Newton meter, means reading on Newton meter, changes by 1 millinewtons. Now we need to find out magnetic flux density B in milliteslas. So first of all, we can simply write down what is given to us. Force is given to us. Force in this case is 1.0 millinewtons. I is given. I is equal to 5.0 amps. And L is also given to us. L means in the magnetic field, that is 6.0 centimeters. We can write down this one in meters. We can say this is 0.06 meters. We have to find out the value of B. Angle between L and B is given. Angle between L and B is given theta, and theta in this case is 50 degrees. So simply we need to find out B. So we can write down magnetic force is equal to BIL sine of theta. Sine of theta. We need to find out B. So we can rearrange this one. B is equal to F over IL sine of 50 degrees. So sine of 50 degrees. Force in this case we will just leave in millinewtons because our answer has to be in milli. So we can simply use this one 1.0. If you want to use in newtons, so we can also use in newtons. So this is how you can write down force in newtons. I is given. I is 5. L is given. That is 0.06 meters. So here we have sine of 50 degrees. Now if we do these calculations, our final answer in this case will be 4.4 times 10 to negative 3 teslas. Or simply we can say this will be equal to 4.4 milliteslas because our answer has to be in milli. So this is our final answer. And this question has 2 marks. The first mark you will get if you have written this formula. So this is the C mark. You will get this one. And the second mark is answer mark if you have got the right answer. So this is answer mark. This is how marks will be awarded. For second part, we need to state with a reason is the change in the reading on the Newton meter and increase or decrease. In first part, it was given to us that reading on Newton meter changes by 1 millinewton. Now question is asking us, is that change is an increase or is that change is a decrease? And that's what we need to find out. So first of all, we need to state and then we need to write down the reason for that. If we say increase, we have to state why increase. So we have to explain with reasoning how it increased. If we say it decreased, then also we need to give a reason for that. This is simply about Fleming left-hand rule. So let's try to understand how we can use Fleming left-hand rule for this question. For this question, it is given to us that PQ just enters the magnetic field. So this is side PQ. And the angle between PQ and B is given. Angle is 50 degrees. So I can simply also say this angle is 50 degrees. But we have to be very clear. B is in the horizontal plane. So B has 2 components. So B is in the horizontal plane. So it has two components. One component is along PQ. So this component has no effect. But one component is perpendicular to PQ. But this is in the horizontal plane. So it simply means that if I redraw PQ, so this is PQ. This side is P and this side is Q. Now it is simply inside a magnetic field that is into the page. So simply you can imagine that there is magnetic field that is into the page. And this wire is placed inside a magnetic field. That magnetic field is into the page. And question is asking us to find direction of force on this. So simply we can say B in this case is into the page. So this is external magnetic field. And I in this case, this is to the right. And we need to find out what is direction of magnetic force. So simply we have to use Fleming left-hand rule. As you can see in this case, current is to the right. So this is direction of current. And this is direction of magnetic field. Magnetic field is into the page. So direction of force, simply you have to use your left hand, but don't use the right hand. This is Fleming left hand rule. So the force will be upwards. So the force is upwards, it means reading will decrease. So simply we can say reading will decrease because the magnetic force is upwards and magnetic force can be found using Fleming left hand rule. Now let me show you the answer. This is how you can write down your answer. This is how you can write down the answer. If you have written this one, you will get 1 mark, and that is the mark. So you have to mention reading decreases and you have to say force on wire is upwards using Fleming left hand rule. So you will get 1 mark for this part. For the last part, it is given to us the frame is lowered further so that the vertical sides start to enter the magnetic field. We need to suggest what effect this will have on the frame. First of all, let's try to understand what does it mean by vertical sides. Vertical sides means this left side and this right side. Current in left side, this is down, current here is up, and current here, this is to the right. Now this frame is inside uniform magnetic field. I will explain you with the help of this loop inside uniform magnetic field, but you can imagine this one by yourself. You can visualize this one, but principle is the same. Now if you look at this magnetic field is to the right, and current on this side, this is down. So this current is down. As you can see here, current is down, but current on this side, this is up. Now if you look at these two sides, there is a force on this side. That force is actually out of the page. As you can see here, this force is out of the page, and force here, because direction of current is reverse, force on this side, this is into the page. So one force is out of the page, one force is into the page. So we can also use symbol here. This means into the page and this force means out of the page. But if you look at the line of action of these two forces, are not along the same line. So it simply means that it will cause rotational effect. In this case, the loop will rotate counterclockwise, CCW, counterclockwise. But if you look at the forces acting on SP, means this side, SP, and forces acting on side QR, these forces are also acting in opposite directions. That if you look at the line of action of the forces is along the same line. So these two forces, they will not cause any rotational effect. So because the line of action of these two forces is along the same line. If you look at the resultant force acting on this loop, mean these four forces, the resultant force will be equal to 0. But the net torque is not equal to 0 because this force out of the page, this force into the page, they will cause rotational effect. And when side, I will just look at side PS. So this is our magnetic field. So when side PS, or we can say side SP, this will be perpendicular to the field. When this side will be perpendicular, you can imagine that when the angle, this angle is theta theta, when this angle will be 90 degrees, actually there will be no torque. So this is the second point you need to understand. First point you need to understand is that you can imagine when this will rotate counterclockwise. Finally, when angle between PS and magnetic field, this is 90 degrees, there will be no net torque because the force here, force is up, here force will be down, and these two forces also will be into the page and out of the page. But that line of action of forces when this angle is 90 degree also will be along the same line. So that time net torque also will be zero. But this loop will continue rotating because it has momentum. Net torque when angle is 90 degrees between SP and the magnetic field is 90 degrees. That time line of action of these two forces and line of action of these two forces will be along the same line. Means these two forces, they will cancel each other. So there will be no torque, and these two forces, one force will be into the page, one will be out of the page. So they will also be along the same line. So they will also cause no torque. So that time net torque will be zero. I hope it is clear to you. Main point you need to understand, when line of action of these two forces is not along the same line, there is a rotational effect. But when line of action of the forces is along the same line, means two opposite forces that they're acting along same line, they will cancel each other. And in that case, there will be no torque. I hope it is clear to you. This question has only 1 mark. You can visualize this one later by yourself, but principle is the same. It has only 1 mark. So let me explain to you how you can write down the answer for this question. And this is how you can write down the answer. If you have written this much, you will get 1 mark. Simply, first thing, frame will rotate. Why frame will rotate? Because line of action of the forces is not along the same line. So there will be rotational effect.